Hello and welcome back to Calculus 1, section 3.7 on chain rule. Thank you. As I mentioned, this will be the most important lecture of your lifetime because we are introducing the most frequent technique to take derivatives. Most of the functions that you will deal with, not just in math, but physics, engineering, and everywhere else, are going to be composite functions. This is a way to take the derivative of function composition, f of g of x. So we'll have to review that first and then go into calculus. So let me just write here in blood first. So chain rule used to take the derivative of composite functions, and you know this either as f composed with g of x, or you know it as f of g of x. So you know it in one of these two forms. Now, before we actually do the calculus and all of the stuff you are paying your money for, right? Let's go back to pre-calculus and understand all we need to know about f of g of x. So function composition as a subtitle. Known as f of g of x. So in short, f of g of x is when you take function g and plug it into each x of f. So f composed with g is f of g of x, and since we are used to looking at f of x, we can clearly see that every x of f is replaced with g. I'm going to write that every x of f is replaced by g. So function composition changes the function, changes the domain of the function, because it changes the nature of the function. It can change the purpose. I'm going to borrow your backpack for a second because it's amazing.
We talked about this when we covered the pre-calculus.
Yes, but here we're going to do this one more time. Now, this backpack, I can see some notebooks in here, so this backpack right now contains books. Now, what I'm going to say is that we can change the entire purpose of the backpack by changing the contents of the backpack. So, a book, or a notebook, or the laptop, or whatever you are using as a student, which is the content of the bag, defines a bag and its purpose. Bag itself has only one function: to hold stuff, right? Now you decide what's going to be inside, and that's g of x. So, notebook has its function to contain your notes, right? Book has its function to contain all of the knowledge that you're supposed to learn in calculus, right? So, all of those parts of g of x, once plugged into what we call f of x, which has different purpose, creates a unit that is now school related. However, you can put the gym gear in here, not the books. It becomes a gym bag. You can put a parachute in here, becomes, right, the bag that contains parachute. You can put a camping equipment to some extent, right? It becomes camping backpack, and so on. So it's not enough just to look at the bag and say, oh, I know exactly what it is. No, you don't, until you look inside and take a look at g of x, which is another function that has its purpose to do something. So to understand what the function composition is, it's very simple. We have a whole bunch of things that have their function, and then we plug all of that into the bag whose function is to hold stuff, right? Now, can you use the bag for something else other than hold stuff? Sure, right? You can use it to start a fire. You don't want to, but you can, right? So those are the ideas. Thank you. So those are the ideas in terms of f of x and g of x and where and how they come together. I also probably gave you another idea on to think about function composition. You take a look at this room, and you know that the purpose of the room is to provide a space so you can do something in it. Now, if you take a look at the content of the room, those desks and chairs and everything else in this room has a function, g of x, because you can use it to sit, right? You can use it to put your stuff and all that. So the content of the room would be g of x, but we can take that g of x out, and this room still has its own original purpose, which is f of x for this room is to hold stuff. You take all of the desks out and chairs out and then the whiteboard and the printer and all this stuff, you take that out of this room and you bring in mats and you start having martial arts classes in here. Well, it becomes a gym, right? In that case, it's a different g of x that you are using the space for, right? So your outer function f of x is still the same, but the content that you plugged in is different, which creates a different use and purpose of the entire composite function. So it's not enough to look just at f. It's not enough to look just at g. You have to look at the combination of both of them and what you get at the end to determine what the whole system is. So now, if I have f of x to be x squared plus sine x, and then I say that g of x is 3 over x, I can use these two functions to create a composite function, f of g of x, and I can also compose the other way, which would be g of f of x. Now, the interesting thing is to also consider and look at the domain of each of these and then the domain of the composition of these two together. So f of g of x will tell us to take f and replace every x with g. So it would be g squared plus sine of g. Now g is 3 over x, and that's going to be squared, plus sine of 3 over x. And what we have at the end over here is what we call function composition. Goal for today is to take the derivative of something like that. We can also figure out g of f of x, where g is the boss and f is the one that gets plugged in. So 3 over f, which is 3 over
X squared plus sine x.
perfect. And we see that the outcome is completely different when you compose them the other way. So this would be a standard problem where you understand that every x of the outer function will be replaced by whatever the inner function is, creating a completely new function whose domain could be different than what you had before. Good. So let's see. F of x is equal to e to the negative x. G of x is equal to x squared. What is f of g of x?
E to the negative x squared.
Good.
Yes.
And what is g of f of x?
E to the negative x squared.
Haha.
E to the negative
Gotcha.
x to the second power. That's the best way I can think
E
of.
to the negative x squared. That's what it is. Okay. Oh.
$1 million question.
E squared to the negative
It's,
2x power.
you are getting there slowly, but yes, that's better.
E to the negative x.
E to the negative 2x. Nice. All right. So now the question is, huh? What? That's the question, right? Yeah, I know. So you see, when you have your g, you are supposed to have f squared, right? F is e to the negative x, and then you have everything squared. And when you have exponent of the exponent, they multiply, which is negative x times 2 is negative 2x. Do we remember that rule? Here, I'll write it over here on the side. Rule which says x to the m to the n is x to the mn. And that's what happened there. I'll put that algebra on the side.
Yeah, no, I understand that much.
Good. Let's do one more problem. And then take a look at actually what we need. 3x squared plus 4 no coughing square root of x plus 2. And then g of x equals to x minus 2. Everything squared. No, that's terrible.
I'll take it. I'll take it.
Nah, just leave it there. Whatever.
Alright. So this is going to be.
Just you want us to find f of g of x and g of
Yes, f of g of x and yes, both of those.
I think I can figure this out now.
Just do it, as Nike would say. Give others the chance.
Alright.
So what should I write? 3
times x minus 2 squared.
times x minus 2 squared plus
4.
square root of x minus 2 plus 2, right?
Yep.
Now we expand everything, so 3, we have x squared minus 4x plus 4 plus 4 square root of x. And then 3x squared minus 12x plus 12 plus 4 root x. All right. What else? Or
3x squared plus 4 root x plus 2 on parentheses. Minus 2.
minus 2. Good.
When we simplify the 3x squared plus 2. No, I don't think.
Yep. That's it. Can't do anything. So I hope you all understand at this point how to compose functions, which is not the skill we actually need.
So,
We need this backwards. You need to be able to decompose functions to take derivatives. So we need to be able to decompose functions, which is the backwards procedure. If I am to give you that some function y is equal to 3e to the negative 4x, let's say plus 6, my question and the skill that you need actually is what is f and what is g? That's the skill that we need for Calculus 1. So what do you think? Yes.
would that be 3e to the x?
Yeah, I think that's
3e to the x?
3e to the x, very good. And what's g?
G Negative 4x plus 6.
Excellent.
Sorry if I interrupted you all the time.
This is the skill we need. Y equals cosine square root of x plus 2. What is f? What is g? Yes. Okay. And what else? What else? Ah, it looks like that this one has another layer, huh? So yes, you are going to run into those functions as well, where you have more than two functions combined, right? Your $10 note has a function, right? You can buy stuff for it, exchange it for goods. Then you put that $10 bill into your wallet, whose function is to hold stuff. And then you put that wallet into the backpack that has a function to hold stuff, right? There you go. It's a triple function composition. Yes?
Why couldn't G have been root x plus 2?
Because root x plus 2 is not a basic function. X plus 2 is a linear function on its own, and square root is a radical function on its own. So it's a still function composition. We don't have to worry when you have a single like this 3 constant multiplied, like this -4 over here multiplied. We don't have to worry about that. But if you have a completely different function sneaking in, yeah, you have to worry about. Some of the problems that the students would really hate is sine cubed x plus, let's say, 3 squared. Yes?
What if for your first one you said that f was 3x, g was e to the x?
It's overkill. We don't need to split on that 3. It's a constant that just multiplies in. And also for derivatives, constants don't matter because you just keep copying, right, constants. So we don't care when the constant is floating around. But if it's a function, the whole function, then it's a big deal. Yes?
The result of this one now is going to be another triple composition.
Triple composition? Okay, we can try triple composition.
So in that case, this is f of g of h of x. F is sine cubed x.
Sine cubed. Sine cubed is not a basic function. Sine x. Okay, so you say sine x over here. What else?
On second thought, I think this will be x squared.
X squared. So scrap this. There's another one. 4. Okay. I like that. It's just that I'll have to scrap all of this now. Nice. The first one is x cubed. And then one inside is sine x. And then the one inside is x squared. And then we need to have another function here, maybe function k or whatever, for x plus 3. 4 levels.
How does the cube not apply to
It applies to everything. It's the first one.
It has to be same.
Order, yes. This is absolutely the order it must be in. Now, if you're having trouble of working out with the cube and the square and all these things, let's just write that sine squared x is the same as sine x everything squared, whose meaning is sine x times sine x. So whether your square is directly on sine or the square is on the parentheses that apply on everything, it means the same thing. If you have sine x squared, that is sine of x times x.
Thank you for explaining this better.
So this is where the all of these things fall and why they are in the order they are. So now you see that because of this first formula here, you can put parentheses around the entire sign and put the cube on top, and that would be the outer function. That's your backpack, the one that you see from the outside. And then you start digging in, right? You see the sine, then the next level in is the square because it's on the entire argument of sine, and then last, x plus 3, that's the bottom. Now, some students say, this is really confusing. I don't see it that way. I'm not a visual learner, and whatever you do with your hands, or even if you told me it's like layers of the onion and you can, peel the outer layer and outer layer, like, okay, fine. There is another way that you can establish the order in which these layers are in, and that is, well, imagine you know what x is. Which order of operations path you would, which path for order of operations you would use to compute this? You see, if I had that x is, let's say, 6, the first thing that I would be computing in this mess is 6 plus 3.
Yeah.
And that has to be the lowest level. The first one you compute. The next level up is your 6 plus 3 is 9, 9 squared is 81. That's your next level up. So you would compute 6 plus 3, then you would compute 9 squared, then you would take sine of 81 radians, and then you would cube whatever that gives you. So this order here simply is also the order in which you would compute. So whether you want to think of this as function decomposition looking at functions, or if you want to say, all right, if my x was 6, then the first thing I would compute is x plus 3, so that's the lowest level. You don't have to put any of these assignments until you are done with all possibilities that you can get. Now we can exercise this idea on a different example. Say, with this E example, right? If I knew that x is equal to 2, I can't compute E. It's not E squared. If I know that x is equal to 2, I first have to compute this exponent. That's why the entire exponent is a single function. If x is equal to 2, I would get negative 2 as the answer. And then that negative 2 is applied to E and multiplied by 3 at the end. So that could be another trick to use to decompose these things. All right, one more and we are done. So say you have y equals 4 over x minus 2 squared plus x. Now that's evil, but we can still deal with it. This is excessive already. Mm-hmm.
Well, no.
It's amazing. You should try it sometime.
Thanks.
All right, did anyone figure out the trick?
Yep. I think I did.
What you are supposed to do to fix the problem so you can actually use function composition? I said fix the problem, yes.
I don't know if this is right, but I tried working backwards. So I said that like k was x minus 2, and then h was x squared, and then g.
But we have that plus x over there. That's the issue.
There we go.
Does that come? You for the plus x.
I know that's what I
It's like
said.
attached.
You can fix that x.
Like make it x over 1. Oh, so it's like, but it's like, so wait,
Well, what do you need?
4.
What do you need to match up?
Oh, do we do like common?
Didn't I suppose?
No, what this x needs to match
Oh, denominator.
so we can do the function composition.
A denominator.
Yeah, so what do I need to do to it to make it the same as denominator? So I can do function composition. I need to subtract the 2 and then I can add 2. And when I do that, I'm creating a unit over here which I can replace. So now, if the inner function is x minus 2, then you have x. No, you can't do it that way. You have to use x minus 2, two functions. X minus 2, and then 4 over x plus 4 over x squared plus x plus 2. There we go. As I said, excessive, no reason, but it can be done. That's the skill that we need. So these problems primarily here. The skill we need in order to be able to do what we call chain rule. Now it's the time to learn chain rule. So the chain rule is taking a rate and breaks that rate into multiple rates. For instance, if you have a rate dy dx, well, that's change of y in respect to x. But then inside of that rule, you insert another rate in between. Say dy, du, and then du dx.
For example, in the textbook, comparing it to. Oh, never mind. I won't interrupt the class with
No.
that unless you think it'd be helpful.
Say it.
So, look in the textbook here, the example of 3 people, Yancy, Yuri, and Zan, they're picking apples. They say that Yancy picks apples 3 times faster than Yuri, and that Yuri picks apples twice as fast as Zan. They want you to find how much faster Yancy picks apples than Zan does.
Yes, so that will be the multiplication of the rates for each. Yes. So you have, if the people are working on, well, that's people picking apples. You can also have, pumps pumping the water out of the pool or a flooded basement or whatever. So you can come up with a lot of applications. The trick is to understand that, see this one? It's the same. And if you cancel that one, you get dy dx. So both sides are equal. You can chain as many rates as you want as long as these ones cancel. So you can go dy dx is equal to dy dA, dA, dB, dB, dC, dC, dx, let's say. These are 4 rates that are all multiplied. And that's all okay, because dA will cancel dA, dB, dB, and dC, dC, and you still have dy dx at the end. So for the chain rule, we can understand that we can have any number of these intermediate functions inside. Now, what do I have? I have the function, remember that I have functions f and g, right?
Yeah.
So if I want to find the derivative of the outer function f in respect to x, but g is in the mix as well. Then I can find df dg and then dg dx. Now this is actually the chain rule that we are learning today. This is one of the forms. We'll have a easier to understand form. But this is chain rule for f of g of x. Note that f is the outer function, just like we always had that f is everything, right? F is the outer function. And then you are taking the derivative in respect to x. But then f depends on g. Remember, the contents of the backpack determines what the backpack is used for. Yes, backpack contains stuff. That's always the same function. But the trick is that the content of the backpack, which is g of x, would ultimately tell you what the backpack is for. Is it a parachute? Is it a camping gear? Is it school backpack or whatever? So now you take the derivative of f in respect to g first, and then you multiply that with the derivative of g in respect to x. Now this form is not really user-friendly. The one form that we actually like to use and use all the time is the derivative of f of x, or f of g of x, is f prime with g plugged in times g prime of x. So this is the formula which we use to calculate stuff. So that would be our main formula. Let's see the way this works. What is the derivative of sine x cubed? Now, what has to happen in your head? Or you can write it down. You have to tell to yourself that f is equal to sine x and g is equal to x cubed. If you are not able to do this, you can't do the problem. So this the function decomposition step is extremely important because that's the first thing you do. You distinguish between f and g. And now you just follow the formula. Technically, what you have is you have not sine x, but you have sine g. Because that's what x cubed plugs in. So what is the derivative of sine g? It's cosine g. And what's g? G is x cubed. Times g prime, which is 3x squared. So this part is f prime of g, and this part is g prime of x. All right, so stare at this for a few moments to make sure that you are following all of the things that are important.
So
So this is your sine g over here,
x cubed is not going to be
and g is
affected.
x cubed. What happened?
So x cubed is not going to be affected by the differentiation.
No, because that's the part, you see, he'll probably be upset, but if I am to drop this backpack in the mud, if I am to paint it, if I am to cut it, right, the stuff that is inside is not affected, right?
Yeah.
It's only the backpack itself, the F,
Yeah.
right, that's affected. But the contents of it are not affected.
All right.
I mean, obviously, the backpack burns or something, then yeah, the stuff inside will burn too. But if I am to paint on the outside, let's say, so your inner function, even if it's multiple composition, all of the inner functions stay untouched. Only the outer function, the outer shell, gets the derivative. So the sine, the derivative of sine is cosine, and then we copy what I call the guts. All right? So you copy the guts. So sine, the derivative of sine is cosine, so the derivative of sine g, see, g is the entire x cubed. So the derivative of sine g is cosine g, and then you plug in x cubed for g, and then you go and you take the derivative of g alone, and you get, now this part, which is called the chain. So that's the first example. Let's see another example. The derivative of square root of, let's say, 4x squared plus 6. What's f, what's g?
I assume that g, yes, I think g would be 4x squared plus 6, wouldn't it?
Yes.
And then f would be root x.
So we'll just call it root g. Because that g gets replaced by what g is, right? So now, what is the derivative of square root of g? Well, derivative of square root of g is the standard 1 over 2 square root of g, which is 4x squared plus 6. That's your g. Times the derivative of g, which is
Would be 8x.
8x.
That's it.
So here is your f prime of g, and here's your g prime of x.
How's it come to that? I don't see how it would become 1 over 2 root
The derivative of square root of x. X is to the 1/2. Right? You drop the exponent down. It's n next to the n minus 1. You drop the exponent down and (3e to the negative x squared plus x minus 1). What is f? What is g?
g. F is 3 yes.
Okay, we'll just call it g. And what's g?
3 negative x squared plus x minus 1.
Good. Guys, I'm not joking. If you don't learn this lecture, you are done. This is the bottom line. No, people usually don't make, professors, instructors, and so on usually don't make these statements like this, blunt. But this is 90% of your problems from today on through Calc 2, Calc 3, differential equation, physics, engineering courses. Most of the functions you see are composite functions, which is why I say if you don't understand this, you better be asking questions. Please do all of the homework available, extra problems. You can find extra lectures and stuff on YouTube as well. See me if you need extra help. But if you don't know this lecture, you are done. It's very simple and to the point. You need to be able to do this fast and efficient. Do you have to write these things? No. If you are able to do this just by looking at it, fine. That's the ultimate goal. But whatever you need to write on a side, whatever you need to do on a side, please just make sure that whatever answer you provide is the correct one. And the last lecture of our course is use substitution for integration, which is the most important integration technique. And if you already guessed it, great for you, it's backwards chain rule. So that's going to be our last week, maybe Tuesday. We're going to see that, and it's going to be backwards this. And it's going to be your main integration technique for a half of Calc 2 and pretty much all of Calc 3. And then differential equations and so on. You absolutely must know this. So what is the derivative of 3e to the g? It's 3e to the g. So you get to copy everything as is, and then you multiply that by the derivative of g, which is
2x plus 1.
plus 1. Yes. Now you can make this nicer by writing it as 3. You can multiply 3 into this, or you can leave it factored. It doesn't matter. You can just make it nicer. So this is your f prime of g, and this is your g prime of x. The derivative of x plus 3 raised to the 93rd power. Are we going to FOIL this?
Yes.
All right. I'll be back on Thursday, 2021.
But this problem here.
You done?
No, I'm not sure how to go about this.
Any ideas? Yes.
This one, x to the 93rd power.
Excellent. We'll just call it g to the 93rd power. And what's g?
Oh,
X plus 3. Great. So what are my derivatives?
X g is 93.
93g to the 92. Right?
Yeah.
Now g is x plus 3, so we're just going to fill that in. Times the derivative of g is 1. Great. So the whole answer, no coughing, is 93 x plus 3 to the 92. Nice. Let's pick some of the homework exercises over here. They have some wonderful stuff you're going to love. Find the derivative in respect to t of cosecant t squared plus t.
you assume there are only two functions here?
Yes.
Okay.
See you next week. So what's the f over here?
Cosecant g.
Cosecant g. Great. And g is?
G squared plus p.
Perfect. All right, let's see what you guys get. What's the derivative of cosecant? Okay, so it will be negative cosecant G
Right.
cotangent G, right?
Yep.
So we start with the negative cosecant G, which is t squared plus t, cotangent G, which is t squared plus t, and then finally times the derivative in respect to t. And what's that?
+1.
Plus 1, nice. I was waiting for that plus 1. So this is f prime in respect to g, and this one over here is g prime in respect to x. So that's one of your homework assignments. Let's take a look at another one. This was problem 38. Let's see what else they have that it's holy nightmare, look at that. Not yet. Let's leave that one to bake for a while.
I'll take it now.
You will? All right.
Sure.
It's his fault. 54. The derivative in respect to x of sine squared of e to the 3x plus 1. Yep.
So there are 3. Not 4. 3, not 4.
He is 4.
Okay, that's yeah.
So you need to have 4 of these in a product. Now you understand why decomposing is a very important skill, right? Hey! What happened?
There's a bug here.
So?
Tolerate this behavior?
I don't care. It's interesting that you're behaving that way.
Yeah.
It's a bug. What is God gonna do? Look at your size. Is that a problem?
Yeah, this is
Let's
my
see.
solution here. Is just one of
So that's the. Oh, so these are your functions over here. So that one squared, and then this one here, and then this one perfect. So you have it decomposed, it's just the execution is not. Because you have to plug in, when you take the square, all of this becomes the guts, as we said.
Yeah.
So it's 2 times, and then you have to write everything. And then cosine of everything. And then e to the whole thing, and then finally times 3 at the end.
Yeah. That's what I did.
You didn't plug in the right things. You did it over here, I see that. But you didn't plug in the right things on this line.
So I'll have the same.
So yeah, we're gonna do it now.
Okay.
Ready?
Sure.
Yes. F, G, H, and we said K, whatever.
Oh boy.
3x plus 1.
Yes.
Okay, so that will be to the K, right?
Yes.
And then
So A to the H.
sine of H in this case, good.
And then
G squared, nice. So technically what we have over here is the derivative of G squared is 2G times the derivative of sine H is cosine H times the derivative of e to the K is still e to the K, and then times the derivative of 3x plus 1 is just 3. So that's technically what we have. But we actually need to plug in all of the functions, right? So 2 times, what's g? G is everything, which is sine of e to the 3x plus 1.
Oh, wait, I thought the values, the values changed.
Well, g contains h, and h contains k, and k contains x, so propagates all the way to the end. Cosine of h, what's h? H is the entire e to the 3x plus 1.
I thought this was,
And then finally e to the k, so that's e to the 3x plus 1,
it's gonna probably just be.
and times 3. Now, problem is technically done. You could write 6 times e times, but there's a much cooler way to simplify this problem. You might recall sine 2x formula as 2 sine x cosine x. You might recall this formula from your tree class. The right side is exactly what you have here. So you can compress this into 3e 3x plus 1 times sine of 2e to the 3x plus 1. That's the boss level. Right? It's the boss level of simplify. Okay. Oh, it's expected in chapter 4. You don't have to worry about it now, but next week, next week, we're already there. And we're going to do one more example and then take a break. When we come back, we'll do the tangent lines and those excessively annoying problems for no reason. We have another problem, and you have a choice between bad and worse. So which one are we going to put on the... Bad? All right. And then you can try worse for homework. 59.
I'd rather do worse now.
you just shoot us with like the hardest thing you have.
Well, you guys just picked bad before the worst one has only one more layer, so the worst one has 3 x's in nested roots. All right, let's see what we get.
Oh, it's doing this now?
What do you think?
We're doing this now.
What do you think? Do that, I do my call. Can you do that? I do Candy Crush, you do that. Once you pass Calculus, then you can do Candy Crush. That's okay, rewrite it. You can try, phone a friend. You look at it in the mind.
This is chapter 4. This step will we have to do.
Oh, it's just in chapter 4, they would like to know what the maximum of this function is, so you have to take the derivative set equal to 0, calculate critical points, do calculate the test and know we can do max. This would be just something that you do in the margin of that. But that's next week, nothing to worry about. How's this corner of the road? This is the panels. Spontaneously combustion. I don't need more than one. for the day.
That's what I mean. Oh, okay, good. I was like, this is like going over my head. That's what I started. They would show it.
Did anyone change all of these roots into halves and then try to do anything? You did? Alright. You got it?
Following the format from earlier. It's root. Sure, something's gonna be 4 over.
So you said this is root of G, and this is root of... What did you say? I said that F was root G, and then I said that G was X plus root H, and then this is H was X. I think that's right. You think it's right? I think it's right. It's just weird. So then I said like, the derivative of root G would be 1 over 2 root X plus root X. And then times G prime of H would be
You don't have to. So actually, this is one of those problems where writing these parts actually makes it more confusing, but such is life. So let's use algebra to rewrite this problem into the derivative of x plus root x raised to 1/2. Would we all agree on this? Now, I'm going to treat all of this as one variable, right? So all I have to deal with now is x to the 1/2, and that would be 1/2 times this mass to the negative 1/2. We are using the basic rule of the exponents when you subtract 1. Now the guts are x plus square root of x. And then we take the derivative of the inside, which is 1 plus 1 over 2 root x. Maybe you memorized by now that the derivative of square root of x is 1 over 2 root x. It's a good thing to memorize. You will see square root of x many times. So it's good to memorize it, even though it's not a basic derivative that you would be memorizing, but it does help because it's so frequent. So now we have 1 over 2 square root of x plus root x times 1 plus 1 over 2 root x. Now, at this point, we don't have to do more math because there are already 2 factors, and if you need to, in chapter 4, set this equal to 0, then you will be setting each one of these equal to 0 and solving from there. So, we don't actually have to simplify this any further because it already has factors and you can set each one to 0 and be done. Can we? Sure. We call that mathematical gymnastics, right? You go and you keep working on this. So guys, this is part 1 of chain rule. We're going to take a break. When we come back, part 2 will deal with tangent line calculations, and then we'll add more stuff to this chain rule in terms of product and quotient rule to make this annoying for no reason.